our last speaker tonight is Fredrik Oskar Christiansen. Fredrik was born in Sweden and studied his undergrad and master's at Gothenburg University. He did his master's project in Zanzibar on the effects of whale-watching boats on bottlenose dolphins. After that, he did his PhD at the University of Aberdeen in Scotland, followed by fieldwork in Iceland, with Marian Rasmussen as his external supervisor. His PhD project looked at the long-term effects of whale watching on minke whales in Faxaflói Bay. After finishing his PhD, Fredrik moved to Deakin University in Australia, where he did research on the movement ecology of sea turtles for 1.5 years. Before, he was approached by Murdoch University in Western Australia, where he spent 4 years studying the effects of human activities on whales, using drones to measure both physiology and behavior of large whales, which Fredrik is presenting today.
Okay, thank you everyone for coming and you listening from home. So this talk was originally going to be about using drones to study whale physiology and behavior, but I realized that was too much for 15 minutes, so I changed behavior to bioenergetics. And to kind of frame the rationale behind this research, I'm interested in looking at the impacts of human activities on marine mammals. And there are two ways that human activities can affect populations. It can either be directly by removing individuals from the populations, which could be, for example, it could be ship collisions, bycatch, or direct whaling. But it could also be indirect effects that have population consequences, such as noise from ships, from whale-watching boats, and also military sonar and so on. And this is the kind of framework that I'm working on to understand how these indirect effects can affect populations. So the rationale is that any kind of stressor, if it's noise or whatever it is, can change the behavior of the animals. And these behavioral changes has energetic consequences. So it can affect how much energy an animal acquire, so how much they're actually getting through their food, and also how much energy they spend, if they're swimming faster or being stressed. And over time, this is going to affect the body condition of the animal or their energy budget over time. And for whales and, well, marine mammals in general, body condition is very important because that will determine how much energy animals has available for reproduction and also to survive. And these are key components when you talk about population dynamics. So I realized when doing research on this, because this was actually the topic of my PhD, which was here in Iceland, I realized that there was not much information on the link between body condition and reproduction and survival or vital rates. So I wanted to go further into trying to study this, but to do that we actually needed some new methodology. But first I have to go back and explain what is actually body condition. Because body condition can be many things. It can be many different physiological index. But what they have in common is that they all describe how much energy reserves an animal has relative to their structural size. So for humans it can be the body weight, it can be the circumference of your stomach or whatever. For whales it can be surface area, the body mass is very common, volume, blubber thickness, because whales have a lot of energy in their blubber, or girth, for example. But it's very important that all of these metrics are standardized against the structural size of the animal. For example, an animal, if you say a human weighs 80 kilos, if the person is 180 long or 160, that makes a big difference. So this is an important detail. So historically, almost all the information we have from physiology and bioenergetics from large whales is from whaling, both commercial and scientific. And there's ethical reasons to like or not like this, but also it's kind of financially costly to do it. It's impossible to get repeated measurements for obvious reasons, and it's not suitable for threatened populations. Other ways you can get physiology data from wild animals is if they strand or they get caught in bycatch. But this can also be quite biased if certain reproductive classes are more likely to strand. And also when the animal dies, the body changes. They fill with gas, they can kind of bloat up, or the weight of the whale itself can kind of deflate the body shape. So in the 1990s, aerial photogrammetry was introduced. We actually take a photograph of an animal from above, and from this you can measure the length and width of the animal and use this as a metric for condition or body condition. And in 2015-16, drones were introduced as a way to take these photographs, which really revolutionized this field because now you could do it in a very cost-effective way. It's also non-invasive, it's not very loud, it's safe because there's no people involved except for when you land and take off. And the most important is you can actually use this to get repeated measurements of the same animal over time, which hasn't been possible. So I'm going to go through the steps now how you actually measure body condition in baleen whales or any marine mammals. You first of all need a drone with a good flat camera lens so you can get a good representation of the body shape of the animal. And then you need a rangefinder that you can actually measure the altitude of the drone above the animals you're photographing so that you can use trigonometry to scale what you're measuring in photographs to actual meters. And this is an example of a southern right whale aerial photograph or from a drone. And it's the kind of ideal picture you want to get, where you can actually see the body contour very clearly of the animal is stretched out. And from these kind of images, you can extract several measurements. You can get the body length of the animals, and what I normally extract is also the width of the animal at regular increments of 5%. So that gives a good representation of the body shape of the animal. And then you can use different metrics to quantify how much the energy reserves or fatness of the whale is. Some that's been used in the past is surface area, where you basically just calculate the area from these different width measurements. You can do it in 3D, so you account also for the depth of the animal, so to calculate the body volume. And you can also take lateral pictures of the animal if they happen to roll over, or if you have underwater footage showing the lateral side of the animal. And then you can get a more realistic kind of elliptical body shape, which you can use to estimate volume. But then, as I mentioned before, it's important to relate this to the structural size of the animal. So what you then do is you plot this metric, or you look at it in relation to, in this case, body length. So you have volume on the y-axis and length on the x-axis. And then you fit a regression line through that, which represents what you would expect the volume of an average individual of a certain size to be. And then any data points that end up above this line means that the animal is in a better than average condition for that population, and anything below it means it's in a poorer condition. So then you have something to actually compare them to. And just to show some examples, I'm working on multiple species around the world and trying to find relationship between body condition and vital rates, as I described earlier in the beginning of the talk. So for the right whale work, which kind of have been the most of what I'm working on, I looked at different aspects. I looked at body condition versus, for example, calf growth. To do this, I'm looking at South Australia, which is a calving ground for southern right whales. They come to this area called Head of the Bight every austral winter, which is our summer. And the animals stay here for a long time. So up to 3 months, you can see the same individual every day. And it's a really good area to study them because that gives you repeated measurements of the same animal over time. And you can identify the individual also from a drone by looking at this unique callosity pattern on their heads. So what I did was I measured the same mother-calf pairs over 3 months period, and then we could actually measure how individual females lose body volume over the whole season, over the winter. And we could at the same time measure how quickly their calves are growing, and then actually compare these two to see how calf growth is affected by maternal body condition and so on. And what we found was that if a female loses condition very quickly, the calf is growing very quick. So that means that the faster a female is losing condition, the more energy she's investing in the calf. And in the next step, we found out as well that what determines the rate of investment by the mother is her absolute size. So how long is she, and also how fat she is. So really long, really fat females will invest a lot of energy into their calves, and they will grow very fast. So it's good to be big and fat. Then we have body condition versus reproductive rates. For this, we did a global comparison of right whales between the southern hemisphere and also with the North Atlantic right whale, which you probably know is critically endangered. It's only about 350 animals left. And whereas the southern population actually growing quite quickly. So the idea was to compare these and see if some of this decline for the North Atlantic right whale could be due to malnutrition. So we used the same approach to measure the whales in a standardized way across all these 4 populations and then compare them. And here you can see the body condition index on the y-axis with 0 indicating average condition. And then you have different reproductive classes, so calves, juveniles, mature, and lactating females. And the different colors corresponds to the different study areas. And what you really need to pay attention to here is the blue lines. So for calves varied a lot in condition, so there was no big difference between them. But juveniles, adults, and lactating females were all in significantly poorer condition in the North Atlantic. And that also corresponds really well with what we now found in a recent paper, that immature whales, or actually the whales in this area is growing very slowly. Mature whales are not reproducing very often, so their reproductive rates are very low. And lactating females that have less condition, we just showed you that they are going to have less energy to invest in their calves. So the calves are going to grow slower and potentially even have a lower survival probability. What you can also do with this kind of technique is to estimate the absolute size of the whale, which you can then use to, for example, estimate energy requirement or metabolic rates and so on. To do this, we tried it again for southern right whales, but in Argentina. And we took pictures of the whales from above and from the side. And then we created these 3D models that we could then relate to old whaling records where you had the length, girth, and actually mass, which is very unusual for right whales. And by relating these to these old metrics, we could recalculate the volume of these whales that they were caught in the 60s, and actually then come up with a conversion from volume to mass to calculate the mass of whales from our aerial photographs. And you can see this curve here. And why is this important? Well, apart from pure bioenergetic interest, you can also use this for applying sedative doses to entangled whales, which happens a lot in the North Atlantic. And in these cases, it's very important to know what the weight of the animal is, so you don't apply too much or too little of these doses. What you can also do, because right whales, as I mentioned, you can identify them from the callosity patterns. And in many areas, they actually come back to the same breeding or calving grounds every 3 or 4 years. You can actually use long-term sighting information where they know the age of these animals and then look at the length of these animals and create lengthed age curves for these different individuals. So you no longer have to rely on whaling records to do this. You can actually do it for free-living whales. And you actually get the calves, which was very seldom recorded in whaling literature. And then by relating this to the old whaling records, we have tissue composition and so on, you can actually calculate the energetic content of the whales and then calculate what the cost of growth throughout their lives will be. And in locations where you have females arrive when they're pregnant and then they give birth, you can also look at the number of days from when they were last observed as pregnant and when they were first observed as with the calf, and recalculate what the size of the calf was at birth, and then see the effect of the maternal size on that. And we actually found a positive relationship. So the larger the female is, the larger the calf is going to be at birth, which is very common in mammals, but it had never really been shown in marine mammals, or not in large whales. And we could even go further and see from females what part of the body actually changed after they gave birth. So if you see this figure here, the x-axis represents the measuring site. So this is the head region of the whale, and this is the tail region of the whale. And this is the change in relative width of the animal over its body. And the blue line is the pregnant females, and the red ones are the lactating ones at different intervals afterwards. And by using this information, we can actually identify which females are pregnant just from aerial photographs. And that's really valuable from a monitoring point of view. Some of you might have heard of the unusual mortality event of the grey whales that's happening at the moment. And we were lucky enough to actually have started a bioenergetic study on this population, not knowing that this unusual mortality event would happen. But we picked it up in our data, and we could actually see that between 2017, which was a normal calving years for this population and not many mortalities, and 2018 and 19, we actually saw a decline in the body condition of all different reproductive classes on the breeding grounds. So again, this method is very useful if you want to look at the health of population and monitoring it in relation to, for example, mortality events. And finally, you can use it to address the cost of migration and so on. This is some of the early work we did on humpback whales in Western Australia, where all this work started. We were up in a breeding ground in Exmouth, and we could look at the rate of loss in condition of different animals over the season, over the breeding season when they're not feeding. We found that lactating females and adults lose most conditions, followed by juveniles and calves. But these were all taken from different animals, so we don't know if is this representative of single individuals. So then we'll try to quantify the absolute loss in conditions. So we went to the southwest corner of Australia and measured the whales just when they arrive to Australia and just when they leave Australia. And we can see the difference here. And actually, when you look at this, you can see the juveniles lose a lot of condition over that period of time, whereas adults surprisingly lose less. We are doing a follow-up study on this now to look at the migratory timing and if this could have an impact on this. But it shows you that, yeah, you can do a lot of things. You can look at trends. You can look at absolute change in energy reserves and so on. And we're also trying this now with a comparison between a feeding ground and a breeding ground, focusing on the Colombian calving grounds and the Western Antarctic Peninsula feeding ground. And then there's also a population of non-migratory humpbacks that you might have heard of. It's in the Arabian Sea. And we're also doing a comparison between that population and a migratory population, which is stock D from Australia, and seeing if this could be how these animals function in different environments. One where you have feeding at half the time of the year, and another one where you could potentially feed and breed throughout the year. And surprisingly enough, we found that the condition of the ones in Oman were surprisingly high, even though the population is only about 100 animals. So we are doing more investigations there to see if there could actually be, how this change seasonally in condition and so on, if there is any seasonal change. But it would be interesting to see how this could actually shape this difference in kind of life history between these populations. And now, finally, we'll be over to Maria, who is starting a PhD here in Iceland, where the idea is to use this methodology, the drone photogrammetry, to look at the energy requirements of various species of cetaceans here in Skjaldfandi Bay, ranging from the smallest harbor porpoise up to the blue whale. And yeah, hopefully she will be standing here next year and presenting this. So. And yeah, this is not me alone. There's a lot of people involved in this project, and although they're not here, I would like to acknowledge all of them. So thank you for listening. I can't see anything, so I guess you have to point.
Hello. Thanks for that. It was really, really interesting. If you, I don't know, let's say if you define like a body condition as like number of calories of energy stored or whatever, do you think that this photogrammetry method captures all of the change in body conditions, so looking at body shape, or do you think there's any sort of like hidden changes in energy storage that can't be captured by this?
So the question was, is this metric of change in body shape or body condition using morphometrics capturing all the changes in body reserves of animals? No, I don't think so. I think it's, and actually that's something we need to investigate, which is very difficult, because it's been shown in a lot of different species, including minke whales and fin whales here in Iceland, that all the different tissues of the body actually changes a lot in both protein and lipid content. And unless this is correlated with changes in girth, yeah, it would not be picked up. And there is definitely a minimum condition at which point the animal will have reached a minimum structural body shape. beyond which you can't see any further change, because you have the bones, you have the structural tissues and so on. And below that, you would never see it. I think some of this can be investigated by looking more into whaling records to see what is the correlation. Is there a correlation or relationship between the girth of animals and the lipid content and of various tissues? So it's a really good question, and I don't think it captures everything, for sure not. So.
Thanks, that was super interesting. Lots of different projects. If you compare, doesn't matter which species really, the body condition that you measure now with the drone, with the old whaling records, do you see big differences in body condition? Do you feel like population, on average, the length has declined, or they're in a better state or in a worse state? Where do you see the most differences? Have you ever compared that?
So the question was, has there been a change in body condition and also body size, I think, between populations a long time ago from whaling records and populations now? Some of it has been investigated. I think there's a lot of potential to do this further. There is been a comparison now in South Africa for right whales. Actually, it was also based on aerial photographs taken in the 80s, using the same technique but from manned airplanes, and comparing it to drone measurements taken in 2019. And there was a massive decline in condition of those animals, which also correlates with a decline in reproductive rates for the same population over the same time, which was interesting. I think in terms of body length, yeah, it would be really interesting to look at this. If you can find reliable records of body length, because that can also be quite tricky from old whaling records, they can be biased. It would be really interesting to see if that have changed, both because they might have targeted larger individuals in the past, but yeah, just to see how it actually is distributed. Because, for example, if you look at guidebooks and so on, you often get measurements of, or data saying a humpback whale can be, 18 meters long or something. I have never measured a humpback whale being 18 meters long, or a right whale being that size either. Like, some of the reported lengths are possibly from whaling records, but we just don't see them anymore. But they might happen because the animals need to get to a certain age. But having said that, a lot of animals are actually quite old now, and I don't know if it's a change in structure or if it's, it needs to be investigated further, is the short answer, yeah.
For the gray whales, when you started detecting like the drop in body condition and unusual mortality, has your data been paired with, other data of what was going on in the ocean at that time?
So the question was, has the decline in condition of the gray whales of Mexico, has that been correlated with other metrics or like environmental change or so on? Not definite, no. They found a relationship using different methods to look at body conditions. So there have been comparisons using visual assessment with the drone assessments. There's also been a decline in the calving rates, which is correlated to this. There hasn't yet been a correlation with the feeding grounds and productivity up there and the body condition. But there has been a paper that was published recently which showed an earlier mortality event was correlated with a lower productivity up in the Canadian feeding grounds. So I think when we have more data on it, because there will be data from there, I think, this is definitely where that research is going. And I think that will help answer it. Because we are not detecting the change in body condition for that population occurs already when the animals reaches the breeding grounds. So we know they're not declining more during the breeding ground. It's happening before. And it's very unlikely it's happening during the migration because there's no change in disturbance on the way. The migration route hasn't changed, so it's most likely something happening on the feeding grounds.
I have a question not very much related to your project, but you mentioned it with the right whales when they, we call it sedate, like put them, I guess, to sleep to disentangle them. How do they do that the whale doesn't drown? Like how
What-
do they do that? Do they just
Yeah, I have never been involved. Oh, sorry. The question was, how do you sedate a right whale without killing it? I don't know. I've never done it myself, but ask the people at Woods Hole. But I think you don't sedate it to the point where it falls asleep. You do it so it becomes more drowsy and slower. So it just means it's easier to approach it. You basically exhaust it, and then it's more manageable to disentangle it. So yeah, I think you do that. How you apply the dose and everything, what you do, how you apply it, I don't know. So.
I think that's it.
All
Thank you
right.
so much.